Good afternoon. Welcome to Comp 422 and Comp 620 Information Privacy and Security. Today we're talking about secure software design. I've got a variety of slides, almost a random selection of slides that I picked up from here and there and someplace else, including several slides from Dr. Yuan. Here is the current schedule. Let's see. You are here. We're talking about secure software development. Note, by the way, there are readings in the textbook. These are in the syllabus. We're on chapters 19 and 20 right now. On Monday, we'll talk about buffer overflow, which is covered in chapter 13.5. And a week from today, we'll be talking about electronic voting or voting security. We have a guest speaker a week from today, Jason Green, who's a PhD student working in the area of election security, will be here to talk to us. And also read section 18.1 of the textbook. Okay. Well, talking about how do vulnerabilities get into software? Well, it's you. All those programmers out there, you're doing it. When you write insecure code, you are leaving the users vulnerable to attack. All the problems that we've talked about and we'll talk about are generally created by programmers who fail to follow good software design methodologies. Of course, you are also the solution. If you do write secure code, then you can protect your users from attack. Basically, security is a software problem. It's a problem of software quality. If you write software that does not have bugs and doesn't fall to the common security problems, then you're basically safe. But if you don't watch out for the common security holes, then you're likely to cause problems. I know several of you out there are not computer programmers and have no intention of ever being a computer programmer, but we need to talk a little bit about programming because that is the source of the problem. So today we're going to talk about how to develop software in a more secure manner. The computer science department has a secure software engineering concentration for the major. It's basically following good principles, creating quality software that is reliable and minimize the number of faults tends to create secure software. There are several reasons why web applications, and most systems now are web applications, have a lot of problems. One is that people aren't watching out for them. Immature security awareness. People aren't always aware. Developers are not always aware of the great risks they are giving to their users by not creating secure software. A lot of web developments are created by the company that's doing it. It's in-house development. And it looks so easy. There are all sorts of packages out there. You can create a website, a web page, in an afternoon, a lot of them, and easy enough. It looks really easy to do. And it is easy to do. Unfortunately, it's not always as easy to do to create it securely. So you have to be careful that when you create these applications, that you follow the rules, you do the things that you have to do to make it secure. And we'll be talking about that today. There are a variety of good software security practices that you have to follow in order to get this. And today, of course, we talk about several, but we will not at all be covering the whole range of things that one might do to make your software more secure. First of all, software development is a whole bunch of things. We'll talk about the development process as a whole life cycle of developing software from first ideas of what the software is supposed to do all the way up to maintenance at the end. And all along the way, you have to think about security. It's useful to know the common problems. Most of the problems we have are not new. Most of the security problems are in the list of the OWASP top 10. If you look at the OWASP top 10 and solve those, then your software is in pretty good shape. You don't have to be very esoteric. You just go for the big commonly known ones. Again, design for security, be secure from the very beginning, and test it. Okay, the software development process. First of all, a confession, I am not a software engineer. I've developed a lot of programs in my life, and I have noticed while working in groups developing software, that software development techniques are very important. Software engineering is important, that you have to do it well, particularly when you're working in a team. If you have a bunch of people working on a project, you have to follow software development protocols. Otherwise, you can end up with a mess. So I read once that if you develop software to use by yourself, it's 9 times more difficult to develop software, the team that's going to be used by anybody on any kind of computer, as opposed to you're going to use it yourself on your own computer. So it becomes much more difficult. And there's a variety of development processes and many agile models. There's all sorts of models for doing it quickly. The software engineering field has changed quite a bit in the last few years, and there's lots of these new ways to do it. Those of us with gray beards, the waterfall model has been out there for decades, and it's still used. It's the old design, and this iterates back. There are some processes that make the iterations more obvious. Development, planning, analysis, evaluation, and so forth. And prototyping, rapid prototyping models go out there. You need to put security at every level. If you omit it at one level, you will be sorry later on. And there are many levels. Requirements, of course, when you first think, what is this software supposed to do? You talk with the intended users and you decide, what do you want the program to do? Design is when you figure out, well, how are you going to make it do that? That's when you talk about, there's several layers to design. If you talk about the big picture, what modules, how is it going to run, the architecture, and you can get down to what are the modules supposed to do. And then you have to make it do that. Implementation is the coding. Somebody has to go out there and convert the design into code. And then once they get it all written, you have to put it all together, which is not as easy as it looks. You may have many pieces, and each piece may work perfectly all by itself, and you put all the pieces together, it may not work at all. That's one of the wonders of software development. And then installation, yes, if you're going to write software that works on multiple systems, you have to be able to install it on that system, which may or may not look like the systems that you use to develop it on. And then maintenance. Sadly, software doesn't work right the first time. And so after you put it out there, the users may discover a problem. Or what also happens besides problems is the users love your product so much, they want it to do more. They go, oh, that's cool, but can you make it do this too? And so you have to add additional features. And the people who put together the software going, yeah, we didn't put this in the first time because we didn't have enough time to do it. But boy, it'd be really cool if we added this. So maintenance is out there. Now, when you find a bug, decide that something's not going to work correctly, how much does it cost to fix it? Well, if you use the cost of one for figuring it out during the design phase, when somebody's reviewing the design and say, oh, this exposes the user to a problem, we need to fix that. If that cost is one, then implementation, the coding cost is 6.5 times that. If you find it in testing, it's 15 times that. And if it's in maintenance, you discover a flaw, it's 100 times the cost of if you fixed it first. So the cost goes way up as you move forward in the development process. So finding and recognizing problems early on is much more cost effective. People have done surveys. Software engineering people like to do lots of surveys and find out what's going on. And so they asked people, when should security be first considered in the software development lifecycle, SDLC? And so they asked developers and security people who had a slightly different idea on this. Here we have the different requirements planning, requirements analysis planning, and so forth. Most of the security people felt that it should be done in requirements analysis. And again, that's the largest area for the developers. Interesting enough, in the planning, security people are way up there, but the developers drop down. Same thing with application design. When you go to development, that's where a lot of the developers think they should be first considering, where security people know that at that point they think it's too late. As you can see, most people think maintenance is far too late to do it. There are a bunch of possible problems, and the problem is getting bigger. Software is becoming vulnerable because we're pumping out a whole lot of it. Some of the problems are, three of them here. One is connectivity. Applications just don't run by themselves. You're connecting to all sorts of other parts to make it work. You're connecting to this and connecting to that, connecting to earlier existing systems, and trying to make all these work. Extensibility, again, plug in. You want to make this thing work everywhere, and it uses all sorts of existing parts, and that makes it more complex. And complexity itself is another problem. The applications are getting bigger, and everything is more integrated with other parts. And so it's code-based course. Even that means you're using lots and lots of existing software to build it. And that's how software should be built. You should not reinvent the wheel. You should use existing software. But in doing so, you open yourself up to more and more security problems. So, what did I just say anyway? So let's try this. First, click a question today. Oh. That's right. This is not hard at all. Oh, anyway, oh. Oh, go on. Oh, all right. We had some people in class who like to vote for B and D, B and D, whereas online people were paying attention. I think A was the answer I was thinking about. Oh, wait a second. Yes, design. Yes, doing it early. If you worry about the problem during the design phase, it's much easier. If we just quickly go back a few slides. Yeah, relative cost. Boy, you want to do a design because if you do it in maintenance, it's going to cost you 100 times more. Okay. Although I usually refer to a problem in the software as a bug, textbook, and there's much of this in the textbook, divides it into three separate categories. We have defects, bugs, and flaws. Defect is something that doesn't quite work right. It, as they say, may lie dormant and bite you later on. Implementation vulnerabilities and design vulnerabilities are defects. A bug is an implementation level problem. A defect can be in many levels, but a bug is an implementation level. And again, you may have a bug out there that never happens. There can be bugs, in other words, you wrote the code, it's not correct, but you've been lucky and either nobody's done that or that problem just hasn't occurred and you haven't seen it. A flaw, as they come, is more subtle, deeper problem. It's often at the design level. Flaw is the way the program was designed. It doesn't quite always work correctly. So a bug is something the coder, usually you think the coder put in there, they didn't code it correctly, it doesn't quite work. A flaw is, oh yeah, that's probably not the right way to do this. That at a higher level, at the design level, they made a mistake. Well, we're talking about software development. A flaw might be you're using a database and it turns out that's not not the proper database to be using. Or let's say you're using a file system and you realize, oh, we should be using a database instead of regular files. That was a mistake. It's not really working the way we want. It's inhibiting our ability to put in bigger fixes. That's a flaw. Okay. Risks. Life is full of risks, and risks are generally result of flaws and bugs. Risk is basically the probability that something will occur times the impact of what it will do, because not every bug is going to cause a problem. Every software defect or bug or flaw is going to cause a big problem. Some of them are just an annoying little thing. Others are major, particularly in the area of security. Others are big holes, and if somebody finds them, they can get all your information. The bad one that people see is somebody's downloaded all the credit cards of your customers along with their personal information. That's a big problem. That's the one that's going to cause you a whole lot of problems. Or someone's going to steal your proprietary source code for your application. That could put your business out of business. So that's the how dangerous is it? What kind of harm is it going to cause? And then there's how likely is it to occur? And of course, risks are not just software. There's all sorts of risks out there. Some of them are technical, some are non-technical, some are managerial, process-wise. Buildings. If they don't lock the doors of the building, somebody might walk right in and steal something. And there's all sorts of errors you can get out there. Well, okay, you can read this in your spare time. I don't get much out of it, so we'll go on. I stole these slides from somebody else. Some of them are from Dr. Yuan, some of them are from the web. Some of them are worthwhile, and some of them, but all of them are true. But yes, okay. Problem application security, and of course it means different things to different people. Idea of application security is keeping that program secure, but the programs don't run by themselves. The programs are part of a bigger system. And so, okay. Where are the slides that I wanted? Okay. As I said, there's more to a software than just a single application. You've got firewalls and networks and all sorts of other things to keep track of. Okay. This in particular came from Dr. Yuan, solving the problem of the 3 pillars of software security. And they've got risk management, software security touch points, and knowledge. We'll talk about all those briefly. Okay, risk management. It's a decision, it's a business level decision. You have to make sure that you make the call that you're going to allocate your resources in the most meaningful way in order to keep the system secure. Companies only have limited resources. Everybody has limited resources. Even your federal government, who seems to have more money than they can print, has limited resources, and they can only do so much. So you have to decide what it is you're going to do and spend your money and your effort and your time there. Here's a chart that I made. You can imagine that there are problems that are easy to fix and difficult to fix. And it may not be easy, difficult. You can imagine a scale. And then how likely is the problem to occur or not? And again, I have likely and unlikely, but you can imagine a range. They can be, yes, this is very likely to occur, or no, this is very unlikely to occur. It might. And then you have the issue of, well, how likely is the problem to occur and how difficult is it to fix? You typically would like to fix the ones that are likely to occur and easy to fix. If it's likely to occur, you better pay attention to it pretty soon. So we have likely to occur, easy to fix as your first priorities, and likely to occur, difficult to fix your second priorities. Spend your effort fixing the problems that are likely to occur, and not spend your effort on the ones that are unlikely to occur, even if they are easy to fix. Some people spin their wheels fixing these little bitty trivial problems, and they fixed a whole bunch of little trivial problems, but they're still extremely vulnerable because they haven't fixed the big ones. Okay, software security touch points. Dr. Yuanda finds a series of areas where you can attach security and measure security at certain parts of the software development life cycle. Okay. And again, it's the full life cycle, all different stages you have to worry about security. Microsoft put a security development life cycle together many years ago. What was that? Oh, gee, 19 years ago. Mandatory policy. I may have a slide about this later on, but I'll waste that slide now and tell you about it. At one point, everybody thought Microsoft Windows was insecure. That was the big thing, that Windows was insecure. Yeah. And common knowledge was that Windows was insecure. And in fact, it wasn't very secure. Bill Gates, the head of Microsoft at the time, he no longer is, he retired as head of Microsoft, but he said, we've got to do something. And so he just stopped all development and had everybody go to courses on secure software development, developed a process and required everybody to use the process. I mean, it was a major stop of the companies. The whole process development stopped and said, everybody pay attention to security. I mean, that's an expensive thing to do when you have thousands of employees, you all of a sudden stop them from working, but he did it because you had to do something. And it's been developed. Okay. Oh, another clicker question. Let's try this clicker question. This one takes a little thinking. Oh, ABCD represents the answers. This is the clicker question. Oh. Yep, okay.
We can't vote online.
Oh, excuse me, you can't?
Yeah, we can't vote online.
Oh, I'm sorry. Okay, now you should be able to. I apologize. I don't know how those buttons work or not work. Right. People should be online. Online's got a pretty good answer here. Let's take a look at this. All right. How do you decide this? Well, I decide this by looking at pairs of answers. Okay, we've got. There we are. Okay, let's compare A and D. They both have the same repair cost. A is much more dangerous than D. So you're going to do A before you do D. That's easy to say. So D is not the answer. For all those who click D, D is not the answer. Then you go, okay, compare A against C. Well, A has greater danger than C, and it's easier to repair. So it's not C. Now we're left with A and B. B is easier to repair. It's a 1. And it's one of those quick fixes that you can go out and, that's what you have interns for. They give it to an intern, tell them to go fix that problem. But it's not a big danger. 4 is, is a significant danger on a 1 to 5 scale. That's pretty serious. So you better take care of A. It's got a danger of 4, repair cost of 3. So you need to take care of that one first. Everybody understand that? Okay. Moving on. Okay. We'll talk about touch points, show some pictures in just a minute. Touch points work in a variety of development models and even your own made-up development models. I'll tell you, places make up all sorts of development models. Okay, here we are. We've got requirements, architectural design, test plans, coding, testing, and feedback or maintenance from the maintenance. And then we have these things you can do. Code review comes in the code. Risk analysis starts in the very beginning, whereas 3. Penetration testing here at the end. Where's 4? Oh, yes, risk-based analysis and testing. Requirements, you think about what can happen. Requirements, of course, security requirements and abuse cases. What might you do? Basic abuse cases means go down the usual list of attacks and see how your design and requirements are impacted by these. And then 7, security operations. They're in order there. Here is the order of those things. Some are more effective than others. So the ones at the top here, code review, claim to be more effective than, say, security operations. Oh, and there's a slide I warned you about way back in January 2002. They spent $300 million, which is a bunch of money, and trained everybody on secure protocol, secure development, because, yes, they had a security problem. And they went out and they fixed it. They spent a lot of time and a lot of money on it and significantly improved the security of their products. They developed a bunch of tools to help doing that. And here's a question about those touch points which you just looked at. Did you really understand what I was saying? I get the hand over the corner. All right. Where's the stop? How come I have a lot of D's? You got to look at their cards when they hold them up. There is no D answer. All right. Folks online are, unfortunately, maybe I didn't make this clear. Nope, the answer is not A, true. Well, okay. Yes, starting security at the earliest levels is very important. The touch points, the list of touch points that Dr. Yuan brought, the most effective ones is code review. Code review happens in the coding stage. The early ones, like abuse cases and security requirements, but those are not always as effective. So we want to look at effective. No, we have a bunch of them, and they have the list there sorted by effectiveness, but the early ones are. On the other hand, the early ones are cost effective. The cost effective doing the early ones are important. What that means is you're more likely sometimes to find problems in different areas. The code review often finds a lot of bugs, Whereas, eh, yes, code review finds bugs, whereas, backing up here in the picture, security requirements may find flaws, and they may be bigger problems if you don't get them fixed than the code reviews. Code reviews are generally more effective at finding problems. Oh, let's just skip the Microsoft software development life cycle. They have a life cycle, spent a lot of effort doing it. There it is. Training, requirements, design, implementation, verification, release, and response. Okay, moving on to 3, which is knowledge based. Yes. Back this one. The answer is one false. Yeah. If what's true is false. Yeah, sorry. Okay. So again, education, continuous process improvement, accountability are big parts of the accountability. That is, somebody is made responsible for this and they hold that responsibility. So if there's a bug, it's their fault. Education was very important in training. Yes, if you got a bunch of programmers, you can't expect them to all know how to develop secure software from the very beginning. You're going to have to teach them. And of course, if you have a new software development lifecycle that incorporates security, you're going to have to get that out there because almost everybody, a lot of people have different software development processes. And so when you go to a company, you have to learn what their process is. And you have to measure it. A lot of people tell you, you can't measure it, you can't fix it. Okay. Okay, so knowledge, people again have to understand what the problems are, what they can do. I shouldn't have borrowed these slides from Dr. Yuan. We'll just go through. There are touch points again. Okay. Moving back. All right. The risks, the rise of security engineering, people are becoming more and more interested in security because more and more people are paying a lot of money due to faults. People are attacking software at a higher and higher rate. All the charts I've shown, the rise of this go up and up and up. And so people are more concerned about keeping their software secure. So you have to work on this from the very beginning during software development. And again, it's much cheaper to prevent than to repair. Because repair is usually done after you've been bitten, after somebody's done something to you, and it's very expensive at that point. Now, I have some slides after this that talk about whose job is it to be secure. And they asked a couple people, or a whole lot of people in different positions, what that was. Basically, it's everybody's job. The builders being the software developments, have to make sure that they build it properly, and they use good programming design tools. Operations people have to use it correctly. Administrators have to understand the nature of the problems and put the resources and decide what problems they're going to chase down. Users also have to understand that software can be secure and that to use it in a secure manner. Okay, here we have some charts where we have developers, development management, and the head of development operations. And here we go. The security of applications is critical to my part of the responsibility. Well, developers didn't really think so, but boy, the managers and development and operations people did. Security considerations to be part of the software development life cycle. Well, the head of operations certainly thought so. Yeah, sort of on the. I understand. Next question. I understand the latest threats to application security. Well, they all sort of thought they did. And then I have access to timely security information. And that is wrong. The programmers didn't think so. The heads of operations thought they did about 2/3 of the time, much more than the developers. That's interesting. Here's a slide on the release of insecure code. Okay, so we have the different groups, developments, operations, and do they release secure code? Well, Managers, about 18% of the time. Here's a combination. This is the average of all the others. So this is, they actually ever released the secure code? Well, 19% of the time, they think they did. In other words, they knew it was going to. Excuse me, that's wrong. That's the other side. Never. 20%, nope, we never put it out the door if it doesn't work. Sometimes, well, 27%, well, sometimes we do if there's a bug, but we don't. Although, actually, that's not sometimes, that's rarely. Sometimes it's 35%, and often it's 20%. So 20% of the time, they think that they often put software out there with a bunch of bugs, which is about the same percentage they think can never put it out there. And then, again, the same groups, developers, managers, and operations. I'm given the time necessary to create secure applications. Developers think about half the time, although the operations people, nope. I understand the latest threats to application security, about 2/3 of the time for most of them. And we learn from our mistakes to develop more secure applications. Well, the developers didn't think so, although the management thought so most of the time. Okay. There are several tools you can use to help look at code and determine if it has any problems. There's static code analysis. Static code analysis looks at the source code. It reads the source code and looks for potential flaws. And it goes there and will tell you all about possible problems. It's what they call static code analysis because they're not actually executing the program. They're simply looking at the source code and trying to determine if there's problem. They look for unsafe functions and a whole bunch of other problems. They're pretty complete in, they look at a lot of different issues. In my experience, they aren't terribly effective. They have a lot of false positives. At least they say, oh, that's dangerous. No, it's not. And they, of course, come for all sorts of programming languages because they look at the source code and therefore their programming language is specific. And the nice thing about them is that you can run them in all your software. If you have a tool, you can then say, run it on every piece of source code you have in your product and see what it says. And it will tell you about the well-known, one of those ones that it knows. And it will go right down and say, on this code, on this line, there's this problem. And so you can run this and have people go back and look at the reports, go back to the code and see, yes, is that a problem that they should fix or maybe not? Problems are, of course, it doesn't always find all the problems. It only, in fact, finds a small percentage of the potential problems. As I mentioned, a high number of false positives. I've run several moments in code and it complains about things that I didn't really think were a problem. And sometimes it's difficult to show that security is actually a security issue is actually a vulnerability. Yes, I'm doing this, but no, it's not going to cause a problem. And a lot of code relies on existing libraries. You're going to use a library function to do something. The library function is not checked by these tools, so you don't really know if that's causing a problem. Okay, we got another clicker question here. Let's try this one. See if you remember what I said earlier. Oops. There we go. Okay, good. Most people said C. C is a good answer. Yes. If you go, I won't go back to the chart, but yes, they release insecure software about 20% of the time. Now, why do they do this? Because they're bums? No, because sometimes they've got it running, it works, and there's a bug out there, and well, what's the risk? Is it a low probability bug? If it's a low probability bug and it's a low harm bug, and you need to get this out because you make your money by putting the software out. They may still put it out. You would be foolish to put out a bug that has a high impact and is likely. Yes, again, functional requirements, you got to make sure that you think about security from the very beginning. Yes, don't do trial and error. Okay, let's go past some of these things. Oh, okay, backing up. All right, sorry, we're going to skip that stuff. I should stop borrowing slides from other faculty members. There is a course in secure software development. Can't remember that Dr. Yuan teaches it. Got some slides for her. If you're interested in this topic, you should definitely take her course. She knows a lot more about it. Obviously, I don't. So go talk to her. All right, but I do know something about this. How about this question, which I didn't talk about, but you ought to know from other courses. Oh, this is a poll question, so let's get the polls open. All right, stop sharing. There we go. What? Stand by. We are trying to figure out what the heck is going on here. Okay, at last. Right. Well, in general, when you delete a file, well, here, let's just, I've got something about that. When you delete a file, the space on the disk that held the data of that file are then put into the free pool on a list of blocks that are available when the system wants to create another file. So there's this big pool of unused space in your disk. At least you hope you have unused space in your disk. And as you delete a file, it just takes the space from that file you deleted and puts it in the pool to be used again. The old operating system does not delete it. Now, it used to be, if you deleted a file, you could go back. There were tools you could boot up, and you would go back and scan the disk, the empty space, for possible files and put them together again. You get back. That's not happening as much because most people are using solid-state disk, these drives. Actually, solid-state disks, that's flash memory disks. They used to have rotating disks that had rotating disks and the heads moving in and out. Those are still out there, but they're not used as often. Solid-state disks are a little bit more expensive, but much, much faster, more reliable. So most machines, particularly laptops, are now using solid-state disks. Solid-state disks have a feature usually called trim, where when you delete a file, the operating system tells the disk hardware that you've deleted these blocks, and then it goes out and flashes them. When you have a solid-state disk, it's flash memory, same kind of memory you have in a flash drive or a thumb drive, and it has to be flashed. In order to write on it, you have to erase the block or flash it. So you have to do the flash operation on the block, which, by the way, flashes the whole block, not just individual bytes, a whole block of it, and then you can write on that block. I might mention also that the flash operation is detrimental to the block, that you can only do it about 100,000 times for a particular block until it wears out and it stops working reliably. So if you have a solid-state disk, you can only flash the block. The people who use these things are no fools. They rotate it around. when you delete a file, it puts it on the end of the queue and takes another one. So it won't be reused again until you've used all the other blocks. But when you allocate a block to a new file and you're going to write on it, if you haven't flashed it before, now you're going to have to flash it and then write. So that makes the first write slower. So most systems, as soon as you delete it, they go out and they flash it when the drive is available. In other words, when you stop reading and writing information, and it has an idle period, and it goes out and flashes the free blocks so that they'll be erased. So then when you want to go write on them, you don't have to flash the first time. So while traditionally on old, well, not that old, the spinning drives, the data is still out there, solid state drives tend to delete them. By the way, if you can look at the options in your solid state drive, if you don't have the trim feature turned on, turn it on. It makes it run faster and run more securely. I have an announcement that I got from A&T in my email today. Anybody you see this announcement? No. Oh, okay. It came out to faculty, sent out to all the faculty, and it does say open to students, but okay, it's a shred. It's Saturday, that's this Saturday from 9 a.m. till noon. You can go out there and give them documents and they will shred them. You can also give them old electronics and they will destroy them. I might mention they have this big thing here in difficult to read. Red on green just doesn't work, folks. But it says, no, university people, do not give your university hardware to this place. University equipment has to be disposed of in the official university process. You got to give it to the surplus equipment people, and they will dispose of it. And surplus equipment people, I believe, erase the drives. At least I hope they do. Because before you dispose of a computer, what should you do to it? Oh, okay. You have to figure a little point there, thinking about that. Got it? Okay. Oh, really? Okay. All right, we have a variety of answers here. Okay. What should you do with an old computer? Well, depends on how secure you want to be. Yeah, you can just delete the files and sensitive information. And for your amateur, that would probably help. Deleting all the files might help too. Reformat the hard drive. Reformatting the hard drive does not erase the data. Reformatting the hard drive just rearranges the table of contents. It rewrites the table of contents. It does not rewrite the data. It changes the file structure. So all the stuff that was out there is still out there. A group of graduate students of another university wrote an interesting paper. They went out to eBay and bought a whole bunch of used disk drives and then looked on them, see what they could find. They found all sorts of interesting information on the drives. So people were just disposing of their old computers and they were leaving all sorts of information. They were looking at the drives with tools that didn't require them to look at it through the file structure. They just scanned over the drive. I like to beat the drive with a hammer technique. That, by the way, works really well. I've used it many times before. Yes, I'll tell you, you get a big hammer, you smack that drive a couple of times, no one's going to get any information off it. There are less violent ways to do it. Yes. There are tools out there that will erase, excuse me. Oh, the answer? I like B, I like D, B to the hard drive, because it depends on how secure you want to be. If you're going to dispose it, meaning no one else is going to use this computer, you're going to, you might want to make sure that nobody else sees what's on your hard drive. I've used the beat it with a hammer technique several times before, In fact, it's very effective. You can be assured you get a big hammer and you smack it a couple times, you'll break that thing into pieces. No one's going to get any information off it. You're okay. But there are other ways to do it, less violent. I could have included this, but I couldn't figure out how to get down to 2 rights and 2 wrongs. So I just, okay. But there are tools to erase your disk at a very low level. Most of these tools, you can download them from the disk manufacturer. Just who made your disk, if it's a Samsung or a Seagate, whoever made your disk drive, go out to their website. You can download a tool. They always have one to manage it, and it will erase the drive. Usually it will write a thumb drive, and you can boot up the thumb drive and then erase the drive. It's kind of hard to erase your C drive while you're using the computer. That doesn't go very far. You can often erase, say you have a C drive and a D drive in your computer, you might be able to erase the D drive while it's running, but it's hard to erase. So you have to boot up and run the tool, and it will erase it. Now, there are rules and standards for erasing disk drive. Typically, they don't think that just one pass erasing it is good enough. The Department of Defense has a standard, 5220-22-M, says you have to do it 3 times. It used to be 7 times, but they've dropped it down to 3 times. And 3 times is once with zeros, right? 0 bits, 0 all the bits. Then it says, go back through it again and set all the bits to 1s. And then it says, use random numbers and go back and write random numbers over it. The reason is sometimes if you just write zeros all over it, which seems like that would do it, you rewrote zeros over it, there may be latent information. In other words, yes, it's 0, but if somebody got out there and really looked carefully, probably was something that's not more than just your computer, but they really scanned it and might say, oh, it's a 0 now, but it used to be a 1. And of course, it depends on who's looking. If the NSA thinks that this information is very important to national security, they are going to look very carefully. So you want to know. So if you want to keep your stuff in the NSA, I'm not sure that you should, but if you did, there's a standard for keeping your information secure. Okay, now I want to go over some information I got from the Computer Emergency Response Team, a secure coding initiative. You can go out to the CERT website or just Google up CERT Secure Coding Initiative, and they have all sorts of coding guidelines. And they had a top 10, which they don't have on their website anymore. I'm going to go over the top 10 things. This is down at the coding level. So let's talk about some real definite things that you might do to keep your software secure. Okay, and a lot of these duplicate stuff that we talked about earlier in the general sort of vague software security engineering sort of stuff. Okay, define security requirements. When you first start, what are the security requirements? What do you want to avoid? You have to look at the main task and say, yes, this could happen to an application like this, and I'm going to make sure that in the development, I'm not going to let that happen. And then, as it goes through, make sure you meet that rule. In other words, if you say we're not going to allow SQL injection, make sure it's coded so it doesn't allow SQL injection. And have requirements so that you can measure it. Again, if you can't measure it, how can you improve it? Model threats. We've been talking about all sorts of threats in this class. There are lists out there that you can find all sorts of places. CERT, OWASP, all have their list of threats. Go down them and say, we're not going to allow any of these to happen. And make sure that you can check them off and say, this is fixed and that's fixed. And of course, risk. You need to decide how risky, how much damage does that cost, and what is the probability that that error will occur. And go out and get the ones that are a high risk, or high danger, low and high probability to be found. Okay, validate your input. We've talked about this before. I talk about this when I teach the freshman how to program. It's very important that you validate your input. And we've talked about never, ever put user input in a place where it's going to be interpreted or executed. That's a mistake. Make sure it's correct. Not only do you look for bad things, but if a user is supposed to enter a number between 1 and 5, we'll make sure they enter a number from 1 and 5. Make sure they don't enter a number from 0 or a negative number or a big number. Make sure it's between 1 and 5. Just takes you a little bit of coding to say, this is 1 and 5. And if it's not, tell the user to do it again. Because the user may have made a simple mistake. They made a finger fumble and they might have put in the wrong data. If you tell them right away, tell them to fix it. Because if you let that bad number go through, later on it may cause problem with your code. It's hard to tell what happened, harder to get here. It generally causes a bigger, more vague, difficult problem. So, more difficult than if you recognize it in the very beginning. And of course, watch out for any external sources, not only things the user entered, command lines, network interfaces, other system variables, any input that comes into your program. Check to make sure it makes sense. And it doesn't take a lot of coding to make sure that these things make sense. If they don't make sense, you got a problem. And not only should you sanitize data that's coming in, sanitize data that's going out. Make sure that you don't send anything that looks bad. And don't release information that you don't want to. Heed compiler warnings. If you're a programmer, you get errors, warnings. A lot of students, well, warning doesn't keep it from compiling and executing. It'll just keep on going. It's all right, it's just a warning. No, the warning was there to tell you that something's wrong. If you have a warning, do something about it. Now, on rare occasions, the warning is incorrect, but usually the warning means something's happening. Do something in your code, fix your code to eliminate the warning. Warnings come from sometimes warnings are not that it doesn't work now, but you're using code that's deprecated and will no longer work in the future. So fix it. And a lot of students and full-time programmers ignore compiler warnings, and it costs them a lot of trouble later on. Keep it simple. We talked about simplicity, simplicity, or as that's Thoreau, as Steve Jobs said, just simplicity. Keep it simple. Simple programs are easier to understand. They're easier to write correctly. If it gets complex, then it's very difficult to understand if it's going to work, particularly single programming modules. If you take a big problem and you break it into many small modules that have small, simple pieces, coders can write those simple pieces with a higher probability that they'll work. If it's very complex and difficult and the programmer has to know all these different things, it's much less likely that it will work. So you got to keep it as simple as you can. Now, some applications are not simple. They are difficult, but you have to work on it so you can try to minimize the difficulty in each individual module. And then, of course, default deny. That is, if you don't know what to do, don't let it happen. Whereas if you're unsure, because a lot of systems, well, it didn't quite work, so we'll just let it go in. Oh, didn't quite get that right. Well, we'll just turn off the security and let it run. That is not a good decision, because sometimes attackers can make something not work. And by making something not work, it will stop security on other ends. They'll somehow mess up your network so you can't go out and check to see if this is secure, or you can't make a check on the validity of something. So you don't make the validity check, you just let it go through. And now they can get something through without the validity check. Fail securely. I think we talked about that last time. Secure failing. I have this example I found. Okay. So make sure you always leave the system in a secure state. Let's look at this code. We have the logical variable is admin. We set it to true because is admin may be needed to do something. By the way, this is sort of pseudocode. I kind of just wrote this. And then we execute it. We have a try-catch block. Try-catch block. For those non-coders, I mean, if there's an error discovered in here, it will go down and execute what's in the catch block. So then we have the code which may fail. This function here, imagine, of course, it's not just a function, it's a whole bunch of code, but in that code, something may go wrong. After that code, we go, oh, if we're a regular user, go back and say we're no longer an administrator. We're assuming that this code, which may fail, needs administrative privileges. So we've turned them on, and then at that. And then, of course, if we have an error, if anything's caught, we'll write to the log, which is what you should do. You should write to the log. But then note, we didn't change is admin. Is admin is still true. So when you get down to the bottom, if there was an error, is admin is true. It only fixes the is admin issue if it works correctly, not if it fails. So that's not failing securely. This is, oh, yes. When it says fail securely, this is an example of code that does not fail securely. Don't do this. Principal least privilege. We talked about this on Monday. Yes. Don't give processes more privileges or humans more privileges than they need to do the job. By giving them more privileges, you make them more vulnerable. That the attacker may be able to use that. If you can imagine an application that gives you things from the database, looks up information and displays it for you, it only needs read access from that database. If you give it full access to that database, then an attacker may somehow manipulate it in order to erase the database or change it. If the user that is running the database, programs that are running on a server run under some user ID. That's not the user ID of the person, but the user ID that runs your web application or your database application. If that user doesn't have the privilege to write to the database, then no matter what the attacker does, they're not going to change the database. So give it these privileges. Remember that external systems may not be secure. Don't always trust. Again, watch the data coming in from other systems. Validate it. Third-party systems can be compromised. That will compromise your system. Defense in depth. Defense in depth is the whole idea that you have more than one check on things. But watch out for, because if you have just one check for a possible error, somebody may be able to get through that. But if you have multiple checks, you're checking for all along the way for things that might go wrong, then you'll be able to stop it at a different point. You're much more secure if you have multiple layers of defense. And again, fix security issues correctly. Sometimes people say, oh, it's broken. So they go, oh, I'll fix it. And they put in a fix, which causes more problems. You got to fix things correctly. And fixes need to be tested. Even important fixes need to be tested, because you have to make sure that your fix fixed the problem and didn't cause other problems. Quality assurance, quality software is less likely to have bugs than software that is written haphazardly. So use all the software development techniques. There's all sorts of tools for testing your software. We'll talk about these in a minute. Penetration testing, we'll talk about later on. Source code audits, that's again, static code review. And then you have reviewers, external reviewers. You know, people who look at your code, who aren't the developers, and check and see if it's secure. Fuzz testing. I'm not a real fan of fuzz testing. Fuzz testing is basically throwing a lot of input at a system and seeing how it responds. That may or may not find it. It all kind of depends on how broad the errors are. Fuzz testing is very good. In other words, if you say enter a number between 1 and 5, fuzz testing will try the numbers between 1 and 5, and we'll try negative numbers, try 0, try large numbers, try maybe the maximum size integer and stuff like that to see if it works. Sometimes more targeted error testing is better than just general fuzz testing. And again, we talked about code checking tools. Static code checkers, go out there and check it. Because typically you can get these static code checkers for free. Some of them are cost. If you are running a software development shop, you might want to pay for some. And then you can run it against everything at a very low cost to you and find out, do you have these problems? Some of them out there are RATS, rough auditing tools, Flaw Finder, others, Yaska, yet another source code analyzer which uses RATS. Okay. Well, that's it for today. Reminder again, this Saturday, they've got a document shredder. Yes, you don't want to leave things in the trash that have personally identifiable information on it. People find it. That's sorry. And the schedule. We were today, secure software development. Yeah, this wasn't my best lecture, but I'll stop stealing slides from other people. On Monday, we're talking about buffer overflow, and warning, I'll be having an assignment come out Monday or Tuesday. And on Wednesday, a week from today, we're going to talk about electronic voting as we come up to voting time. Well, we're here in Guilford County. Some places are voting, but most of Guilford County, including the city of Greensboro, will not be voting this November 7th, but a lot of places do vote. We're having a guest speaker, Jason Green, who is a PhD candidate working in the area of election security, will be here to talk to you. So you get somebody who knows what he's talking about. So that's a week from today. That's it. Any questions? Then we're done. And we'll see you next week.
Have a great weekend.